Good morning. You might get the impression from our discussion of van der Waals forces and surface tension and capillary forces that the only forces between surfaces and nanoparticles are attractive. In the next two lectures, today and Thursday, I hope to convince you that that's not true. I mean, why would there be any stable colloids if every force were attractive? So you buy milk at the store, and if it's got milk fat globules in it, if it's anything other than skim milk, and why does it not just coagulate into a mess? Of course, it does eventually, but that's the action of bacteria, and changing actually some of the interparticle forces that we're talking about, namely reducing them. In fact, the only reason we have stable colloids at all is because of repulsive forces. If everything were attractive, everything would just be balled up. The last time I'm going to use that in the class. So this is chapter 14. Has anybody tried to read chapter 14? It's long. It's about 60 pages. And we are going to cover it in 78 minutes. And there's way too much in there than we can possibly cover in this course. So my goal is to show you where it comes from, where the electric double layer force comes from conceptually, and how to use the equations so that you can calculate the forces with the EDL force. Okay, if we take, let's take milk fat globules, for example. I got this from a book titled Introduction to Dairy Chemistry. Seriously. And we have these globules in suspension. So this is stable. Combination of the attractive force. The attractive force is counterbalanced by a repulsive force. In the case where the repulsive force isn't strong enough, the particles flocculate. Flocculation can be reversible. It is possible to resuspend these particles given the appropriate treatment. And then we have something that's potentially more catastrophic, which is coagulation, where there might be some mechanical intermixing of the parts of the colloid that makes the colloidal particles that make them impossible to break up again. Just a point of nomenclature: a single particle is not a colloid; it is a colloidal particle. The whole solution is a colloid. The whole colloid is a colloid. So there's this colloid particle doesn't really work by the nomenclature of colloid science. Okay, so imagine these are milk fat globules, and the potential energy between these particles is some addition of the van der Waals force and the electric double layer force, and perhaps something else as well. So this is WD total, which is made up of an attractive component of WD van der Waals plus a repulsive component from WD EDL. It turns out that the electric double layer force, which we mentioned earlier in the class, perhaps the first day of class, which is the result of a cloud of counterions, a diffuse layer of counterions around a particle that are entropically, because when particles approach together are entropically confined, or they're confined, and they want to push the particles back away from each other so that they can enjoy more configurational entropy. So it's an entropic repulsion. We'll talk about more details about how it arises in a moment. But it turns out that the EDL force is relatively weak in milk fat globules. So the van der Waals force in whole milk would tend to suck all the particles together, and you would get a flocculated or coagulated milk. So it turns out that this is not the only part of the total interaction energy. There are also little polymer chains on the milk fat globules, so little protein chains that also exert an entropic repulsion. When you take two milk fat globules and you push them closer together, the polymer chains get constricted, and because they want to increase their entropic freedom, the particles get pushed apart. So there's another repulsive term that is actually required for the stability of a colloid like milk and also other biocolloidal suspensions. So actually both of these are repulsive. But if you look at just the van der Waals and the EDL force, this together is called the DLVO force, which is the van der Waals force plus the EDL force is the DLVO force. And the DLVO force, the first D is der Jagen. I had to write this down this year. Landau, Verwey, and Overbeek. That's what DLVO stands for. But I won't be testing that, obviously. Now, the DLVO force can be thought of a little bit like a Lennard-Jones potential. It doesn't look like a Lennard-Jones potential, but it's sort of like the master potential from which most colloidal interactions are described, just like something that looks sort of like a Lennard-Jones potential is sort of the master potential that combines the steric repulsive force to the Pauli exclusion principle and the van der Waals force due to the combination of Keesom, London, and Debye. In the case of DLVO, you get the attractive forces from the van der Waals force as it was before in the Lennard-Jones potential, and the repulsive force is actually the EDL force. Now, of course, if you try to smash two colloidal particles into each other, you'll again get a repulsion due to the Pauli exclusion principle, but we're generally not gonna worry about that when we're talking about colloidal suspensions. Okay, what do you need to get an EDL force? You need charges at the surface. So is every object charged? Do things just go around like electric monopoles? In air, generally not so much, but in water, generally yes. In water, essentially everything you put in water acquires some surface charge for one reason or another. So EDL forces in aqueous AQ environments And how does this happen? You could have ionization of surface groups. You know, every molecule that you put in water has some, you know, collection of surface molecules on the surface, obviously, that have some pKa that could be either protonated or deprotonated by water, even if there's nothing else in the water except for hydronium and hydroxide ions plus all the neutral water molecules. You could have adsorption of ions to previously uncharged surfaces. It turns out that if you put a hydrophobic solute into water, it's actually the hydroxide ions that stick to the hydrophobic surface. I don't know if this is really known, if this is understood from a theoretical basis, but you can measure it. The surface charge taken on by hydrophobic solutes is generally, hydrophobic and non-ionizable solutes is generally negative due to the adsorption of hydroxide ions. And then it actually becomes the hydronium ions that counterbalance the charge that are the mobile counterions that form this, this electric double layer. Another thing you could have is a formal charge transfer. Or an acid base reaction. So what if you had, in the case of charge transfer, some oxidation reduction at the surface that caused something that was previously uncharged to become charged, or some formal acid-base reaction, could be Lewis acid, for example, attached to some group at the surface to give you a formal charge. Okay, let's consider the architecture of an electric double layer. Let's say that has some bound charges that are negative. And there will be some counterions. And just a little bit of nomenclature here. This distance, again, is capital D. The permanently bound charges, the charges that are intrinsic to the surface, the first charges that are either chemically bound to the surface or the first charges to adsorb to the surface, are called the co-ions. The layer closest to the surface is called the Stern or Helmholtz layer. The whole thing is called the diffuse layer, and And all of these ions collectively are called counterions. Okay, keeping this in mind, what does the distribution of charges, the voltage, and the electric field look like given this counterion distribution? Where again, the separation here between the two sides is D. This curve is rho as a function of x, and the axes are as follows. These are x equals minus d over 2. The midplane is x equals 0, and the right-hand plane, the right-hand surface is x equals d, d over 2, positive d over 2. So this, let me write this over here actually. Sorry for those of you writing in pen. This plot is rho as a function of x, which is the density, just the number density in the solution. At the midplane, we'll call it rho 0, rho naught. And at the surface, we'll call it rho sub s. Now the charge, this distribution of counterions gives rise to a voltage, a potential difference profile that looks like this. And we'll call it psi of x, where psi at 0 is the voltage at the midplane, and psi sub s is the surface charge potential. What does the electric field look like? The electric field is given by the negative derivative of the potential function. So this is E sub x equals minus d psi dx, where we have E0 at the midplane and ES at the edge. What are the midplane values? X equals 0, psi 0 equals 0, rho equals rho naught. D psi dx at 0 equals 0. So we can calculate. What we want to do is come up with an expression to calculate the counterion density at any point x. And to do that, we need the Nernst equation, which is gives us the density of charges due to a generic electric field. And then we need something called the Poisson equation, which gives us the distribution of counterions in a given. It gives us the potential energy field produced by a given distribution of counterions. Okay. So the chemical potential of a counterion is the chemical potential of any species in physical chemistry is usually just the density. So chemical potential is if there's a high density of something that's mobile in some area, a low density in some other area, the molecules want to move from high density to a low density. They want to get away from each other to maximize their configurational entropy. But if you have charged species, there's an extra term, which is because the chemical potential is also dependent on the charge. So highly charged things have high potentials. So there are two parts to the chemical potential. The electrostatic part. This is the electrostatic self-energy. Z is the valency. So for example, calcium 2 plus Z equals 2. Psi is the potential, the voltage, and E is the fundamental charge. Plus we have the usual bit, which is KT, natural log of the number density. So at equilibrium, which is always what we're talking about, mu is the same everywhere. It doesn't mean that so you can have molecules that drift away from the surface, but the chemical potential has to be the same for every ion. So we have a density profile. That follows the Nernst equation. And we learned the Nernst equation in chapter 2. This is equation 2.14 in the book. And this gives us rho equals rho naught times e to the minus ze psi over kt, and this gives us the counterion density in any generic field, any generic electric field. We also need another equation called the Poisson equation, which is Z E rho equals minus epsilon naught epsilon times the second derivative of the electric field. So this is the Poisson equation for the net excess charge density at point X. What this does is it takes into account that when we combine these two equations, it takes into account that this electric field is produced by the counterion density. It may seem a little counterintuitive at first because we're starting out with two charged surfaces. So shouldn't there be an electric field between two charged surfaces? Turns out the answer is no, if they have the same charge and if they're sufficiently close together. But it's the distribution of counterions themselves that produces the electric field that determines the distribution of counterions. So this is related to the potential energy field So the goal is to get the potential energy field produced by a given distribution of counter ions. And if we combine these equations, we get the Poisson-Boltzmann equation. Which is d squared psi over dx squared equals minus ze rho over epsilon naught epsilon equals minus ze rho naught epsilon times e to the minus ze rho over kt. And this gives us psi e equals minus d psi dx and rho at any point in the gap. We are not going to try to solve this differential equation on an exam, but we do need to know what the distribution of counterions looks like. I basically drew it up here already. And if you were to solve this for rho, we get rho naught plus epsilon naught epsilon over 2 kt d psi dx evaluated at x squared. So let's make this a little bit abstract, a little bit less abstract. What is the counterion profile what is the qualitative shape of the counterion profile? For surface charge density sigma equals 0.2 coulombs per square meter and a distance of 2 nanometers. This, by the way, gives you 1 charge per 0.8 square nanometers, so moderately charged. And this will be x in nanometers, and we have 0 here, minus 1 here, plus 1 here. And we'll plot the density in terms of concentration in moles per liter on the left axis, and the concentration in terms of density, so just per cubic meter on the right-hand axis. And this is what it looks like. And what are some values? We'll have maybe 12 molar at the surface, and maybe we'll have, not maybe, these are the answers that you get if you plug in the numbers, and you have 10 to the 28 molecules per cubic meter at the surface in units of number density. Okay, why do the counterions accumulate at the surfaces? Because the charge of the surface. Anyone want to disagree with that? Is there an electric field? Take 2 parallel plate capacitors that are really close to each other. But instead of charging them oppositely, you charge them the same with the same charge. Is there a field between the parallel plate capacitors? Is there an electric field? No, there's not. So if you have 2 parallel plates that are big compared to the separation, and they're positively charged, if you put a negative charge in the middle, it's going to go like this. It will not be sucked to one side or the other by because there's no electric field. If you need to convince yourself of this, try to draw electric field lines between 2 parallel plates that have the same charge. Where are they going to go? So the same thing happens when you're talking about very small distances, like nanometers, between colloidal particles that are big compared to the separation between them. If you take out all the counterions, there's no electric field. You only get the electric field because of the distribution of counterions. That's what the Poisson equation tells you. So what is the origin of the counterion distribution? Imagine these are plates, parallel plates with like charge. And the change in electric field, the change in voltage when going from one side to the other, which is the electric field, d psi dx equals 0, or E equals 0 in the gap. that is a lone charge feels no force. A lone charge feels no force in the gap. You can drop an electron right in the middle here, and as long as this distance is short compared to its length, it'll just float around. And what if you put two in there? What if you put two electrons in there? Then what happens? They will separate. This is similar to the case where perhaps in second quarter physics, you remember that the charge of a metallic object is all at the surface, right? And that's because of internal repulsion of the charges. The same thing is actually happening here. If you put, suppose you had some spherical void that was positive all the way around, and you put some negative charge in here, it would just float around. But if you put two charges in, they would want to get as far away from each other as they could. If you put three charges in, they'd want to get as far away from each other as they could. If you put a bajillion charges in, they'd all want to get as far away from each other as they could. And that's really the lowest energy way to arrange this system, even though it means you're crowding them at the edges. Okay, so this is the first of three conceptually challenging elements of today's lecture. The second one comes right now, and that is the origin of the repulsive pressure. Okay, so if we continue to add charges that are these counterions into this gap, they will be close to the surface, but they won't be completely, they'll be close to the surface, but they won't be completely butting up against the surface. Some of them will, but a lot of them will drift away. And why is that? Because of the Nernst equation, which is a special case of the Boltzmann distribution, which says that if you increase the temperature, you get more entropic freedom, and the charges will drift away from the surface a little bit. They'll still be pushed apart by each other in the gap, but there will be some drift away from the surface. And the drift away from the surface, as minuscule as that is the whole key to colloidal stability. So what is the origin of the repulsive pressure? So we have an electrically neutral system. We have big particles with lots of little charges surrounded by lots of little charges that are mobile compared to the big one. It's like Winnie the Pooh with a cloud of bees around his head because he's eaten honey. He'll move slowly, but the bees will move quickly. So in the case where one species is in an electrically neutral system, where one species is mobile, the other species is relatively stationary, the net effect is a repulsive pressure, actually. What about the case where they're the same size? The positive and the negative charge are the same size, like sodium chloride, is actually a net attractive effect. So the repulsion is actually due to, even though it's an electrically neutral system, the repulsion is actually due to the fact that the counterions are diffuse. They're allowed to escape from the surfaces a little bit. So case one, for considering overall neutral systems, case one, positive and negative are same size. For example, sodium chloride. Electrostatics favor attraction. But what about if the positive and negative are different sizes, vastly different sizes? And the counterions are mobile. In the case where the counterions, or where the two surfaces are relatively far apart, we have this diffuse double layer, where due to non-zero temperature, we have some Boltzmann distribution away from the surface of the counterions. But then if you push these things together, there's nowhere for the counterions to go. And there's therefore an entropic repulsion. Entropic, sometimes called osmotic. This explains the stability of colloids. One of the repulsive pieces that contributes to the stability of colloids, but in most cases it's the most important one. Certainly can't not have this. So it explains the stability of colloids, at least in aqueous systems, and the slipperiness of soap. Why would it explain the slipperiness of soap? So if you have a really dilute soap solution and you rub your fingers together, it feels slippery, right? Why does that happen? Because the hydrophobic tail groups of the soap molecules, the amphiphilic molecules, sometimes SDS, some detergent molecule, will associate with the hydrophobic parts of your finger, and the hydrophilic parts, the sulfate groups, will point into the water, and then the sodium ions, so the sulfates are the co-ions, the sodium ions are the counterions, and they'll float away from the surface a little bit. And as you rub your fingers together, there's actually an osmotic repulsion of the sodium ions that push your fingers apart. Now, there's also the effect of viscosity of thin wetting films of water. And if you have really concentrated soap and you don't squeeze every last molecule except for the last few out, then you're really doing a viscosity measure. Why it's slippery, but with very dilute solutions and very close separations, actually this is why soap feels slippery. Okay, let's look at van der Waals forces plus the EDL forces. And van der Waals plus EDL equals DLVO. In addition to the homework, I would also like you to look at worked example 14.5 in the book. And it will help you to use figure 14.10, which is, for those of you watching at home, don't worry about what this says. 14.10 is really like it's an analogous system to the van der Waals system, where we had two small molecules, two flat surfaces, two spheres of different sizes, a sphere on a flat surface, two cylinders parallel, a cylinder on a flat surface, and two cylinders crossed. So lots of different scenarios in here where they have solved for the electric double layer force between these different geometries. So what you do is you take, if you have some system and you want to get the total interaction potential, you take the van der Waals equation from chapter 13 for two spheres or two flat surfaces or whatever. You add the electric double layer repulsion, and that's the total energy, unless there's something else in the system. And once you add these curves together, what do you get? And we know that there's some electric double layer repulsion, and there's some van der Waals attraction. At small enough distances, the van der Waals forces win out. So if you push the colloids way too close together, they will eventually flocculate. But they won't pass through each other because of the Pauli exclusion principle. So really, there's this other, highly repulsive potential that's really close to the surface, but we're not going to worry about that. Now, a stable colloid has a DLVO curve that has a very large energy barrier that prevents flocculation. You get this with high sigma, which is the surface charge density. It's not the hard sphere diameter in the second part of the course. It's the surface charge density. And you get this with low electrolyte concentration, which we're going to just abbreviate as salt in brackets, which indicate concentration. This bit down here is called the primary minimum. Then there is a secondary minimum, where a stable colloid lives. What if we have a lower surface charge density and we have a very high salt concentration? What happens to this curve? We might get something like this. Low surface charge density high salt concentration. Let's consider some of the take-home messages from this from the DLVO curves. The first is that highly charged surfaces in low electrolyte concentrations we'll learn in a moment this gives us something called a large Debye length, known as kappa to the -1, have a strong repulsive barrier. And you get a secondary minimum where a stable colloid will stay. Now, where is this secondary minimum? Depending on the system, somewhere in the single nanometer range for D. But below some critical surface charge potential, psi naught, or above electrolyte concentration, particles will flocculate. At very low surface charge potential or surface charge density or surface potential, you're going to have strong attractive forces at all separations. And your potential function will just basically become the van der Waals potential function, and you can forget that the last 56 minutes ever happened. Okay, how would you do this? I'm just going to set up 14 Point 10, I'm not going to do it out for you because it's also in the book. You have two spheres. Interacting at some distance d with a radius 100 nanometers, and you're given 100 millimolar sodium chloride electrolyte, and you are given some Debye screening length. So in this table of the EDL energies and forces for different geometries, this is 14.10, you're going to have two variables which are kind of unfamiliar. There's kappa to the minus 1, which is the Debye length, and you calculate it by the square root of epsilon naught epsilon kT over 2 times the concentration of ions in bulk solution times the fundamental charge squared. Or for monovalent electrolytes like sodium chloride, this simplifies, since most of this crap are constants, to 0.304 times 10 to the minus 9 over the concentration in units of molar. Well, without the units, just the value here. This whole thing has units of meters because this is a length. This is the Debye length. And it's usually, often it's going to be given. And we're given a Debye length of 0.955 nanometers. So if we're calculating the energy, we actually have to calculate the force in this problem. But if we're calculating the energy, or you could calculate the force or the energy and have extra fun. The energy is going to be 1/2 R capital Z e to the minus kappa d plus AR over 12D. This does not equal 0.95 nanometers. This is the EDL term, and this is the, I'm sorry, this should be minus. Should be minus AR over 12D. And this is the van der Waals term. And you just read these off a table. So you read these off the tables that you would be given because somebody else calculated them for you. EDLs tend to have this form. Van der Waals tend to have this form. Now what's this Z parameter? The Z parameter embodies everything about the surface charge density. And it has a very complicated equation from which you calculate it. Not complicated, but long. And it is sort of analogous to, so Z is to the electric double layer force as A is to the van der Waals force. And because this chapter is 60 pages and we need to move on with our lives, I'm just going to write down how to calculate Z. Z has the creative name of the EDL interaction constant. and it is 64 pi epsilon naught epsilon kT over E, the fundamental charge, squared, hypertangent squared, of ZE times the surface charge potential over 4 kT, and this has units of joules per meter. At physiological temperatures, since often when we deal with DLVO forces, we're often dealing with pharmaceutical suspensions, drugs in particles, biological systems in general. In general, we want to be able to predict the stability of something under physiological conditions. So at 310 Kelvin, this simplifies because a lot of this stuff is a constant. We have 9.38 times 10 to the minus 11 hypertangent squared of the surface charge density, which is still a variable, over 107 joules per meter. And this, if you're going to use this version of the equation, make sure to remember that the surface charge density is in millivolts. None of this will make any sense until you do the problems in the homework and problem 14.10 in the book, and then you'll see. But really what you're doing is plugging and chugging. There are equations for the van der Waals force for different geometries. There's the EDL force for different geometries. You add them together and you plug in what's given. Yeah.
How come it's given at 310 Kelvin and not 298?
Because this is physiological conditions. There's also an equation in there for, in the book for 298K. All right, so this is now, I'm going to tell you the third difficult conceptual bit from today's lecture. And the first was, there's no electric field in the gap between two surfaces with like charge if the separation is small enough. And nobody fought me on that. I was very happy to see that. Usually we have like a couple of people or like one person who's like, no, there must be a field. You draw a line coming from a positive charge and where does it go? There must be a field. But we didn't have a person like that this year. That's great. And then the second thing was the fact that the counterion distribution is what causes the entropic, or is what causes the repulsion, not the fact that the two surfaces have the same charge, which you would consider normally to cause the electrostatic repulsion, in the absence of counterions, which balance the charges. The third thing that's weird, why would stuff come out of solution if you add salt? Have you ever had a lab experience where you salt something out of solution? You add salt. I need to salt that out of solution. Salt it out. Salt it out. If you haven't heard it yet, you're going to hear it at some point if you work in aqueous media ever. Why does that happen? Why should adding salt cause a colloidal suspension to be unstable? Okay, so imagine those are the worst equal spheres I've ever drawn. Remember there was that point in high school math, where you learned what a chord and a tangent and all that stuff was. And I had a math teacher in high school who must have been double jointed in the elbow, because he could use his arm like a compass and like draw a circle and he must have had to draw like 100 or 1,000 circles in that class. Anyway, comes with practice. It sucks. In the case where we have low salt concentrations, and assume that these have some charge and this has the same charge, same surface charge, same charge due to the co-ions. And I'm just going to represent the counter ions as dots. And we're going to have a diffuse double layer, just as we talked about. But since we have some excess ions due to the fact that we're in an electrolyte solution, we're going to draw all of the other like-charged ions somewhere else. Like, we don't care if the ones on the surface came from hydroxide or chloride or whatever. All the ions are the same once you dump in the salt. We're just considering these dots are the counter ions in solution that have the opposite charge to the surface charge. So if this is positive, all of these dots are negative. There could be more negatives out here than there are positives on the surface because we have extra salt in this system. If you calculate the Debye screening length, you might get something that's pretty long, like that. That's way too large than it should be. Should probably be like this, but I just want to emphasize it's long. It's the long Debye length. In medium salt concentration, you have all of these counter ions in the bulk. Solution. And you have counter ions at the surface as well. But because you have more counter ions to begin with, it doesn't cost you as much entropically for some of the counter ions to sit closer to the surface than they did in the case of low salt concentration. Because we have so many more counter ions to begin with in the solution, there's a lot more entropic degrees of freedom. So you have a lot more places where these ions can be. So it's okay, you don't lose as much by confining yourself to the surface if you're a counter ion. It's like, my entropy is okay, well, there's no such thing as the entropy of a single particle. But it's okay that I lower the entropy of the system because there are so many other places for things like me to be that the overall entropy is going to be pretty high. So as you add more salt, there's less of a penalty for ions to be drawn to the surfaces. So the Debye length, which is can be thought of as the characteristic thickness of the diffuse double layer, is smaller. And notice I drew the separation here smaller because these are now allowed to get closer together because there's less entropic repulsion with a thinner double layer. Now let's go crazy with the salt. We'll go like McDonald's level with the salt. Okay, so here are the ions in the bulk solution, and you'll note there are a lot of them. Now, because there are so many, it barely costs us anything to put ions as close as we possibly can get them to the surface. So there's so many more ions and so many more places that they could be that entropically, who cares if some of them are at the surface? Are exactly at the surface. So the double layer shrinks. Now, kappa to the -1 is tiny. So the electric double layer shrinks. As you add more salt. Now, what is the origin of the repulsive force but the confinement of this diffuse double layer? If the diffuse double layer is thin to begin with, then you don't lose that much entropy by bringing surfaces close together because the double layer is so thin. You make it thin by adding the salt. So there are two compounded entropic effects here. One is that it doesn't matter, really these balls should be gigantic compared to the separation between them, just as they've always been, but I'm just trying to show this to you. If you have, say this was no salt concentration, we would have this diffuse double layer around the surface, we add more salt, the ions could be in a lot more places because there are a lot more ions. So it's okay that they become closer to the surface. And then in a really saturated solution, it doesn't matter at all. Like the counter ions will just sit right on the surface, double layer shrinks. And you can think of the double layer as almost like a repulsive, like tractor beam in sci-fi. Like it's like this halo of stay away from me, where the two particles, you start to constrict the electric double layer and then the particles want to get farther apart again. Does that make sense? So my goals for today's lecture were to show you conceptually where the electric double layer force comes from, which comes from this combination of three sort of unintuitive effects. One is that there's no electric field in a gap between two like-charged particles. The electric field arises due to the counter-ion distribution, and the distribution is a result of two things. It is the result of electrostatic repulsion between the counter-ions rather than attraction to the surfaces. And it's diffuse because at any finite temperature, you'll always have the mobile charges with the freedom to drift away a little bit. And then the third bit is that if you add more electrolyte to the solution, you don't lose as much entropy by confining the ions closer to the surface, and therefore the thickness of the electric double layer goes down, and the repulsive force due to the electric double layer goes down. And the van der Waals forces can take over. That's why you can salt something out of solution. For those of you that haven't heard that, you will eventually in your professional careers. And then, so where does the EDL force come from? And then the second goal for today is how do you use it? You use it by adding the potential or force function to the force function or potential function for the van der Waals force to get the total electric double layer force. You construct a curve, or you look at a curve and you know which one's more or less stable, how to get between them, and how do you calculate the energies and the forces using the Debye screening length and the Z parameter, and you plug those directly into the equations. So you could probably take a whole course only on DLVO forces, which would be mostly electric double layer forces. I hope that you got enough out of this particular lecture to be able to use it on your own. Once I have an announcement after the camera's off and the podcast is off.